Someone is asking for the recording. We already started the recording now, so
Very good.
2 more minutes to go. I would like to ask, please, all the guests, except the speakers, turn your camera off because we are expecting a large number of attendees and the quality of the connection might be affected. So if you don't mind, please switch your camera off. Okay, I think we can start now. So welcome everyone to our GeoTalk-005 in the series. And I will be your host for today. Myself is Hamzah Al-Hashemi from Geotechnical Engineers GCC. If you haven't subscribed to our platform in the LinkedIn, please do. And we are glad to have all of you today. We have a remarkable attendees for this event with over 500 registered geotechnical engineers and students. Before starting introducing our speakers and the moderator, I'd like to share this piece of information with you. Actually, we have asked ChatGPT the following question: if someone to be the father of Piled Rafts Foundation in geotechnical engineering, who will be? And the answer was, in geotechnical engineering, the concept of the Piled Raft Foundation, which is a combination of raft foundation and pines, has been studied and developed by various researchers over the years. However, one name that stands out in this area is Dr. Harry Poulos. Dr. Poulos has contributed extensively to the understanding, design, and analysis of piled raft foundation. His work have offered significant insights into the interaction effects between the raft and the piles and how to optimize the design of such foundations. He has also contributed to the development of the design methods and guidelines for piled rafts. Therefore, if one were to assign the title of Father of Piled Rafts Foundation in geotechnical engineering, Dr. Harry Poulos would be a strong contender for that recognition. So having this being said, I will introduce Professor Harry Poulos. He has graduated from University of Sydney in civil engineering. His career spanning over 6 decades, and his roles varies between the academic and the industry. He's also a senior geotechnical consultant in Tetra Tech Coffey in Australia. He has participated and designed several foundations for several world's largest buildings and structures, including Burj Khalifa in Dubai. He has several and remarkable publications, including 4 books and over 400 technical papers. He has given the prestigious Rankin Lecture in UK, also Terzaghi Lecture in the USA. He holds Kevin Nash Gold Medal and recently Lifetime Achievement Medal from the International Society of Soil Mechanics and Geotechnical Engineering. He is also a membership fellow in Australian Academy of Science, a fellow in Australian Academy of Technology and Engineering, foreign members at the US National Academy of Engineering. He's an honored fellow of Engineers Australia and distinguished member at the American Society of Civil Engineers. I will also
You are muted, Hamzah. You muted just.
So I have missed. Okay. So I will repeat. Okay. So as I was mentioning that we have asked ChatGPT the question that who will be the father of Piled Rafts Foundation, and the short answer was Dr. Harry Poulos would be a strong contender for that recognition. And to introduce Professor Harry Poulos, he's graduated from University of Sydney in civil engineering. His career spanning over 6 decades with roles varies between academy and industry. He's also a senior geotechnical consultant in Tetra Tech Coffey. He has participated, led, and designed several foundation projects for the world's largest structures and buildings, including Dubai. His publications includes 4 books and over 400 technical papers. He also have given the prestigious Rankin Lecture in the UK, Terzaghi Lecture in the USA. He holds Kevin Nash Gold Medal and recently Lifetime Achievement Medal from the International Society of Soil Mechanics and Geotechnical Engineers. He is also a membership fellow of Australian Academy of Science, fellow of Australian Academy of Technology and Engineering, a foreign member at the US National.
Hello? Again muted, the last part, Hamzah. I don't know why you...
I think maybe by mistake, if someone is admitting the people, there is mute all. So yeah. So allow me now to introduce our moderator, Dr. Marwan Al-Zaylaie. Dr. Marwan Al-Zaylaie is a senior geotechnical manager at Dubai Development Authority, adjunct faculty at Hirwood Dubai and Abu Dhabi University with over 20 years of experience. He has several publications and he was a PhD student in TU Darmstadt with Professor Katzenbach. He is a publications also with our guest and keynote speaker, Professor Harry Poulos. Without any further ado, Professor Harry, with great pleasure, please the stage is yours. And for everyone, as housekeeping rules, please keep yourself muted. Ask any question you want in the chat box, and we will have a panel discussion after the guest speaking, and we will answer those questions. The event will be recorded, and there will be certificates followed by the event. Professor Hari, if you unmute yourself, it is muted.
Okay. Can you hear me now? Sorry, can you hear me now?
Yes, we
do.
do.
Yes, we can.
Oh, very good. Well, thank you again, Hamzah, and thank you, Dr. Marwan, for moderating this session. I must say it's very gratifying that there's been such a big response to this talk, and I think this is a reflection of the level of geotechnical activity and interest in this fact that in the not too distant future that this interest will be leading to the development of a new society of the International Society for Soil Mechanics and Geotechnical Engineering. The subject of my talk is one that I've been
Professor Hari, you please unmute yourself. I think let's keep unmuting.
Yeah, okay.
Yep. Yeah.
Yes. So in this subject for over 50 years, firstly as an academic and a researcher, and then in the last 20 or 30 years as a practitioner and a designer. So I'm going to try and share my screen now, and perhaps you can tell me if you can see this or not. Are you able to see my screen?
Not yet.
Right. I may need some help with just a moment, with the control here. Is there a share screen somewhere that I need to press?
Yeah, it should be on the top right, I think.
Top share. There we go. Okay.
Yep.
So yes, sorry, I lost the location. So can you see the screen now?
Not yet.
Is it visible now? Not yet.
No, not yet. And just a reminder, please, everyone, turn your camera off to have a stable connection, please, including ourselves as well. We will, because it seems that attendees are keep increasing, which might affect the connection.
Sorry, let me just find the right one here. I apologize for this. Just trying to see what I can share with you. The screen, here we go.
Yep, now we can see it.
You can see my screen. So, right. Are we right now?
Yes.
Very good. This is the topic of my talk, and I'm going to try and cover these issues. Firstly, just a discussion about how piled rafts work, the mechanics of rafts interacting with, talk about the design concepts and some of the design issues that we need to consider, and how we can estimate overall I'll talk about the design then for localized behavior under columns and try and set out an approach for deciding when you need piles under a particular column. We'll talk about the very important issue of the that are important, and then I'm a number of examples of applications to tall buildings, and I hope that in each of these examples there will be lessons that I will from them. Now, I think everybody will be familiar with these three foundation options that we normally have. The foundation, which can be suitable answers for low to mid-rise soils. Piled foundations, of course, are a very traditional form of deep foundation, but in the last 30 or 40 years, we've developed a combination of both of those, the piled raft, and it combines the better features of each of those options, single foundation system. Now, the design philosophy tends to be a little bit different from normal piles. We aim to share the load between the raft and the piles, and the piles really take generally the majority of load, but the capacity, and so we tend to focus more on stiffness and settlement than on the actual capacity of the foundation, because this is often the deciding criterion. Now, there is another perspective that we can take with piled rafts, and that's to look at the piled raft as a pile-enhanced raft that we prove its performance by acting or adding a number of piles, and the piles then act as load reducers, that they actually carry the load, and even if the pile capacity is fully mobilized, then the pile can act as a spring and carry some of the load, and so it reduces. And so this is the basic way that we can look at it. Now, the piled raft is not a universal solution to every problem, but there are circumstances where piled rafts are extremely suitable, and that is where the raft itself a reasonable amount of stiffness and load capacity. And this occurs if you have, for example, relatively stiff clay profiles, as they have in the city of Frankfurt in Germany, or where you have relatively dense sands or weak rocks. And these are conditions that you have here in Dubai and in other parts of the Middle East. It's preferable that you don't have a situation where ground movements due to external causes can occur. So that's circumstances. There are circumstances that are unfavourable, where you have, for example, soft clays near the surface, where there are compressible layers at depth, where consolidation settlements may occur so that the soil may tend to move away. Lifting movements where the soil itself may cause uplift loading on the piles. So just be aware that we're not talking about a universal solution, but we are talking about a solution that for many cases is extremely favourable, and certainly in your part of the world, these favourable solutions are quite. Now, some of the earliest learnings we had were from small-scale model tests that were carried out in the 1950s by Dr. Whitaker. And these two diagrams show the results of model tests where on the vertical axis is the settlement of the model pile group, and on the horizontal axis is the number of piles, the square of the number.
Professor Hari, sorry,
yes.
It seems there was someone who shared his screen. Please do not share your screen. Do not share your screen and keep your camera off. Please, Professor Hari, if you can reshare your screen again.
Yes, sorry, I'll out again, and
And I saw someone is trying to record the event. The event will be recorded, so please do not record the event from your end. It might slow down the connection. Yes, now we see it again.
Again? Okay.
Yep. Yes.
All right. Important point here that I want to make, and it is an important point with respect to the design of piled rafts, is that piles in the group increases, we tend to get a reduction in settlement, which is what you would expect. But there comes a point at which there is little or no further reduction, and that is when the group itself is such that it acts as a block. So if the piles are very closely spaced, then really the piles and the soil between them act as a single block. And so there is an optimum number of efficiency of a group of piles or a piled raft. And that's an important thing to remember, and we'll come back to that later. Of rafts and piles, first, that the ultimate geotechnical capacity of a piled raft depends if you have widely spaced pile, capacity is the sum of the single pile capacity plus the capacity of the raft. But if you have closely spaced piles, then the ultimate capacity is the capacity of the block plus any external raft area. So for widely spaced piles, and this is where piled rafts become really quite contagious. If you can generate a single pile failure mechanism, you get a greater efficiency of the group, a bigger capacity than you would otherwise. And another is that if the raft is in contact with the ground, it will increase the stress in the ground, and it will increase the height on the ground, and that will in turn cause an increase in the skin friction. Yes.
Sorry to cut you off. Can you please turn your camera off? It seems we have some disconnecting. So if you can turn it off, it might get better.
Okay. Sorry, I didn't realize I had my camera on, so forgive me. I'll just try and do that.
That's okay. We tried, but it seems because the connection is or the attendees are heavy, we have issues. You can access it from the Teams itself, and you can see beside the mic.
Oh, hang on just a moment. I'm plagued with technical problems today. So, sorry, just I need to turn my camera off, right?
Yep. Yes, from this button. Yep. Exactly.
Good. So we'll try again.
Yeah. Thank you. Thank you.
Okay. Yeah, so as I was saying, one of the hidden benefits, and it's one that we generally don't take into account in design, is that the capacity of the piled raft can be increased because of the additional stress that the raft imposes on the ground, and that results in an increase and therefore an pile capacity. And this is an issue, and I won't go into too much detail here because we're losing a bit of time. But Dr. Katzenbach, Professor Katzenbach, show clearly that whereas a single pile may have this distribution of skin friction I'm showing on the right-hand side, a pile within a group of piled raft can have a substantially greater capacity, and that, of course, is a benefit. Now, the other thing that we need to understand is that the settlement depends on the load, of course, on the piles, on the ground stiffness, and on the group dimensions and the number of piles, and on the raft dimensions and the raft stiffness. It's also very important to understand that we have 4 interactions among the elements of the piles interacting with other piles through the soil. We have one part of the raft interacting with another part through the soil. We have the raft interacting with the piles and the piles interacting with the raft. And all of these interactions need to be considered if we're to get an accurate assessment of how the piled raft works. And I'll show you later on in one of the examples how important it is to take account of all these interactions. Moving on now to the design issues, obviously this, as with all foundations, involves considering the ultimate load capacity under the combination of vertical, lateral and moment loadings. Also then looking at maximum settlements and differential settlements, and then from a structural viewpoint, looking at the bending moments in the raft and the shears in the raft and the pile loads and bending moments. So all of these are issues that we have to address. And just one diagram here that comes from our Italian colleagues, and that is that they have identified that once we get to relatively large foundations, for example, for a building rather than perhaps for a bridge pier, then the critical factor for design is not bearing capacity, but it tends to be more settlement. And so we find that the design of the piled raft for normal sort of buildings and larger buildings is controlled by settlement and differential settlement rather than by ultimate capacity. Now, in our practice, we have various stages of design. We do a preliminary design to try and estimate the number of piles required for both capacity and settlement requirements, and then to also assess where the piles are best located. And then, of course, we get into detailed design where we refine the pile locations, we optimize the raft thickness, and we obtain detailed settlement, bending moment, and pile load data. And here we interact very closely with our structural designers because they, of course, provide us with the loads and we provide them with the stiffness values of the and the raft. Now, in terms of preliminary design, this is when we first start off. We need to have fairly straightforward, simple methods. So for estimating the ultimate load capacity, we generally take that as being the lesser of the raft plus the individual piles, or the block of piles plus soil plus the raft outside the block perimeter. And as I've noted here, we need to consider the effects of soil layering. When we're estimating the overall load settlement behavior, we can use simple hand or computer methods, and we can also allow, if necessary, for cases where the piles are fully work, has given us a means of getting a helpful first estimate of the load sharing between the raft and the piles. And so this enables us to get an estimate of the required number of piles to satisfy ultimate capacity and settlement criteria. Now, we've developed what we call a Poulos-Davis-Randolph method. It gives a very simple approach to getting a trilinear load settlement curve. And this requires estimates of the settlement, the group the ultimate pile group and raft capacities, and the raft pile interaction factor. And again, with that, I'll refer you to Professor Randolph's 1994 state-of-the-art single unit of a pile plus a segment of a raft. And we can use the expressions that Randolph obtained to obtain this sort of fairly simple load settlement curve. And on the vertical axis, we have load, and on the horizontal axis, we have settlement. And there are three parts to this load settlement curve. The first part from to a point A1 is where partially behave elastically so that the piles are working and the raft is working together. Now, when we get to a certain capacity can be fully mobilized, and then if we load beyond that, then the remaining load is carried by the raft, and so you get a more part of the load settlement curve until we reach the ultimate capacity of the piled raft system at point B. And so that's a very, very simple trilinear, three-linear part load settlement curve. Now, I have this diagram here, not for you to try and explain it in detail, but for those of you who want to get hold of, it tells you the basics of how we actually get that three-part load settlement curve. And it is something that you do with mathematical programs such as MathCAD. And this is the one that you can develop with that simple, very simple analysis. On the left-hand side, we have the ultimate capacity versus the number of piles for a particular case, and you can see the piles, we have the capacity of the raft. As we increase the number of piles, then we get an increase in the capacity of the piled raft. At the end, you see we call block failure, and then there is no improvement in the capacity of the piled raft if we add. We don't need to add, in this case, any more than piles. On the right-hand diagram, you see the settlement versus the number of piles. And alone, and in this case, it would settle almost 70 millimeters. But if you add even a relatively small number, that settlement down to half or less than half of the settlement of the raft alone. But again, increasing the number of piles, there comes a point where there is no additional benefit. And so in this case, 24 piles or so would be the optimum. The work of Randolph can also be used to give us a differential settlements, and there's an expression that ran of piles, the spacing of the piles, and a first estimate of the ratio of the maximum differential settlement to the average settlement of the piled raft. We now move on to, again, this is in the trying to work out when do we require a pile under a column. And there are four circumstances where you would require a pile. Firstly, if the exceeds the allowable bending moment, then it will help if you put in a pile there under the column to help reduce the bending moment. Where the maximum shear exceeds the allowable shear, so you get what we call punching shear, pile will be helpful. Where the maximum contact pressure exceeds the allowable bearing capacity of the soil, or where the local settlement exceeds the allowable value, so that you don't have a change in the settlement profile. And this is the sort of simple case that we analyze, that we have hits on a layered soil profile, and we need to what the maximum bending moment is in the raft, what the maximum shear is, what the maximum pressure is, and what the local settlement is. We need to develop for that localized design a profile of the soil within an effective depth of 3 times this characteristic length, which is given by this equation here. And again, limitations. I won't go into too much detail, but those parameters are fairly straightforward. Stiffness of the soil, stiffness of the raft and Poisson's ratios, and the thickness of the raft. And then that will give you a characteristic length of the raft. And you get results that are not that well recognized, but very useful, that the late Professor Selvadurai published in his book in 19 a series of graphs that we can develop that will give the maximum column load that we can have in order to not exceed. So you can do that also for the shear, the punching shear, for the local bearing pressure, and for the local settlement. And so there's a paper I wrote more than 20 years ago, which gives the details of how you can use those charts of Selvadurais to get that local line. And so a pile then needs to be put if the column load exceeds any of those critical limit, shear or contact pressure requirement. The pile needs to be designed to provide the deficiency in load capacity provide on its own. And if it's settlement, then the pile need to provide the additional stiffness that is required to reduce the settlement under that column. Loads, just finally, the maximum column load without a pile thickness increases, or as the ultimate bearing pressure increases, or as the soil modulus increases. So raft thickness is in fact very important for local design, and it's something again that our structural college and work out. Now, when it comes to detailed design, then we have certain requirements. With properly for interaction between the piles and the raft, we need to be able to consider practical soil profiles, not ultra. So to incorporate non-linearity in the soil raft after non-uniform loadings, and perhaps different pile types and sizes at different locations below the raft. And so there's a couple of called GASP and GARP that do that. And each of these involve the raft either as a series of strips and the piles are modeled as non-linear interacting springs, the stiffness of which we calculate from elastic theory. There is, over the last 3 or 4 years, a program called ELPLA, which has been by engineers in your commercially available via GeoTech software. And so that's a very helpful program. Now, just to compare what we get with one of the programs I use, GARP, versus a simple. Here is a simple case of a raft with 3 piles, 15 piles. The full line is the analysis with GARP, and the approximate PDR, the trilinear. You see that you get quite a reasonably good agreement between the computer analysis with GARP analysis with the PDR method. So the PDR method does seem to give a reasonable sort of result. Now, in the later stages of design, and we need to consider we have a number of rigorous computer methods. PLAC, for example, Plaxis 2D, RS2, and for full 3-dimensional analyses, which are being we have FLAC 3D, Plaxis 3D, and RS3. And as I will show you in a minute, be very careful when you're using 2-dimensional analyses rather deceptive and inaccurate. And so if you're going to use a complex analysis for a piled raft system, then it's preferable to use a full three-dimensional analysis. A relatively simple problem, we have a raft and a series of column loads, and we have a number of piles, that layer of soil. And all I wanted to show a comparison between the load settlement behavior of the raft with 9 piles, where we have the load on the vertical axis and the settlement on the horizontal. I have 5 curves here. Curve 1 is the PDR method. That's the more or less the simple trilinear method. 2 is the gap analysis, GESP analysis. 4, this one here, is the FLAC 2D analysis, and 5 is the FLAC 3D analysis. And you can see that the two-dimensional analyses give you pretty close agreement, which is pretty remarkable because the PDR method takes about 10 minutes. The three-dimensional FLAC analysis took, I think, about 3 days. So you see that you can get a pretty reasonable, quick answer with a very simple sort of method. But the two-dimensional method is not very reliable. It overestimates the settlement because it's assuming infinitely in the third direction. The other important thing that comes out of this is that if you ignore the interactions that I mentioned before, then you can get a very deceptive values of the stiffness of the piled raft. The correct results, or the accurate results, I show for 9 piles and follow, see that, for example, for the 15 piles, we have a stiffness of 600 or so meganewton meter. So for the group interactions, then the calculated stiffness increases to 600. So that's a 50% increase in stiffness. So your settlements would be reduced by 1/3, include no interactions, and if you entirely ignore interactions, you would have a stiffness value of about 1900, and so that is about 4 to 5 times the correct value. So the inclusion of interaction effects is essential, and the two-dimensional analysis, as I mentioned, is. Now, very briefly, I just need to mention a couple of other side issues. I've talked so far about vertical loading, and this is often the critical to be aware that piled rafts have to resist lateral and moment loading. And it turns out, and you can analyze this particularly with the more complex methods of analysis, but it turns out that the lateral load or proportion than the vertical load, but you need to do a full dimensional analysis to get at the final design stage. I've just got here a diagram which I won't try and explain because of time, but it does show you that for fairly widely spaced piles, you can get quite from the raft being in contact with the soil. In addition, we almost always, particularly with tall buildings, have basement walls. And in a benefit to take these walls into account because they do take some of the horizontal load, some of the bending moment and shear on your piles. There is also the possibility that, and this is perhaps attractive for cases where you have predominantly vertical load, you can disconnect the piles from the raft so that it is ground reinforcement. That has a benefit in terms of improving the overall stiffness of the ground, and it means that you may have less bending moment in the piles. But if you've got significant lateral loads, as you have with tall buildings, then I think is not an ideal solution. Really briefly now to the important issue of the geotechnical parameter assessment. The parameters that we need to make decisions on are the raft bearing capacity, the pile stiffness for the raft action, and the soil stiffness for the piles under both vertical and lateral loading. For preliminary design, often we have to use with simple data such as standard penetration or cone penetration data, or if we're dealing with rocks with unconfined compressive strength. For final, important if you can to do larger scale pile load tests and interpret those to get these sort of parameters. But for a preliminary design, these are the sort of correlations which we can use for raft capacity, pile shaft and base capacity, and for the soil modulus for the raft. And if we're dealing with unconfined compressive strength correlations, these are some of the correlations that can be used. Paper, Dr. Marwan and I and our colleagues have suggested some updated correlations here, which are some of these, and they are based on substantial amounts of data taken from the Dubai area. Now, just a quick measure to take to reduce risks, not only for piled rafts, but really for all types of foundation design. Ideally, we need to have an independent peer review report and an independent peer review of foundation design itself. Ideally, we need to have independent supervision of foundation construction because we need to try and ensure that what is being constructed is in accordance with the design intent. We need to have testing, so pile and barrette testing, and we need, importantly, to monitor settlements during and after construction so that we can compare measured and predicted performance. In particular, if there is a problem, the sooner we identify that problem, sooner and take corrective measures. And there have been cases, unfortunately, where those measurements or the realization of problems was done too late, and that has caused major issues and in some cases demolition. So really we need to treat these measures. They cost money, but really they should be treated as insurance investments and not as costs. So let me now move on to examples of piled raft. And I'm going to talk, and again, I won't be able to go into too much detail about these 6 projects, one in Australia, one in Jeddah, one in Incheon, South Korea, and then a couple of cases, other people's cases, which indicate there is a potential for foundation economy. And in each of these cases, there are lessons that I think we can learn. So this is the first case with some 15 or so years ago, a 28-story building on the Gold Coast in Queensland in Australia, and a structural engineer designed a fully piled they had 140 or so piles going right down to rock, fairly long piles, over 30 metres long. And we were engaged when in the earlier part of the company's history as Coffey International. We were asked to assess the feasibility based on the results. The piling contractor engaged us to actually optimize the piled raft design, and economize quite significantly on the number of piles. This is a layout of the foundation system. Again, I won't go too deeply into it, but here is a case of sand and gravel. There was a peaty sand layer here, but the rock was way down here at this depth, and that was the original design. What we were able to do, in fact, where the piles were substantially shorter and not bearing on rock. And the analysis that we did, that we had a substantial factor of safety in terms of ultimate capacity. So the settlements were going to be the governing issue, and it was estimated between 35 to 60 millimeters. Now, it turned out that the foundation up actually with a little less than 140 piles, but the length of the piles was about half of the original 5 meters. And we were given criteria for the structural engineer: a maximum settlement of 50 millimeters, maximum differential settlement of 1 in 400. And we did this. We assessed the forces, moments, and so on in the raft. And the final solution was a 0.8 meter thick raft, 136 piles with piles, that's continuous flight auger piles or auger cast piles, 18 meters long, 0.7 meters in diameter, have 2 meganewtons. This is a diagram showing the settlement contours, showing that, of course, we get the maximum settlements as we go out. From that, we get decreasing settlements. But all of those settlements, the maximum settlement was about 36 millimeters. The maximum settlement was equivalent to 1 in 400. And so the outcome was that by looking at the piled raft option rather than the fully piled option, we reduced the number of piles by 8%, but importantly, we reduced the length from 35 to 18. We reduced the pile length totally by over 2.5% saving in the foundation costs, and the criteria was satisfied. The Burj Khalifa now with this, but it had a number of challenges some 20 years ago when we started on this. It was to be, and still is, the world's tallest building, which is a foundation capacity for piles and carbonate soils and rocks. Concerns about the effect of cyclic loading on that load capacity. And we also had concerns, as we so often do, with tall towers, that there was a potential for difference in the larger settlements under the high-rise area and the smaller area. So there was a substantial site characterization here, 30 boreholes, many SPTs, and cross-hole tomography, a geophysical, which did two things. It provided us with an assessment of the site uniformity, and luckily it was, but it also provided us with values of small strain shear modulus, which we could then use as a means of assessment. This is a simple of the ground, and I think many of you will be aware that
Professor Harry, you are muted. Can you unmute yourself, please? Oh. Still muted, Professor. Still muted. If you can go to the Teams and on the mic sign, if you press on it, it will unmute.
I don't seem to be. Oh,
Yes,
can you hear me
yes,
now?
yes. Now it's okay.
Hello.
Yep, we hear you, Prof.
Can you hear me?
Yes,
I've
yes,
unmuted
we
my
do.
mic.
Yep. No, it's muted again. It's muted again.
Are you able to hear me?
Yes, now we do.
Can you hear me now?
Yes, yes, we do.
Okay.
Professor.
Right.
Yep.
Sorry about that. We seem to be plagued by muting problems. Okay. So let me continue then. The initial pile design was done by Hyder Engineering in the UK, and we acted as the geotechnical peer reviewers, but we worked very closely together. The tower design was 196 piles, 1.5 meter diameter, 47.5 meters long, and around that were many smaller diameter piles, 30 meters long. The raft itself was 3.7 meters thick. And here we managed to make use of learnings from the Emirates towers, where we had overestimated the settlements. So we were able to refine our settlement predictions using the learnings from the Emirates towers. Now, both Hyder and ourselves did independent estimates of the settlement of the tower. Hyder used two programs, Repute and Abacus, and got reasonably similar results. We used two of our own, the FLAC program, axisymmetric, and one of our own programs, and got very similar settlements. And subsequently, I did a very, very simple equivalent peer check and got an almost. There was, I think that independent peer review process gave us confidence to be within allowable bounds. And load test program that was carried out, it's shown here that there were full-size piles with 3 lengths of pile. There was one static compression test with shaft growth of the pile, a cyclic compression test, a static tension test, and a lateral load test. And in all cases, the results exceeded expectations. We had and larger stiffness than we had assumed in design. So all of that was very positive. And then as construction was done, and these were very comprehensive. And as of February 2008, when the building was around 80 to 85% complete, we had this contour plan of the settlements showing that the maximum settlements, we went away on each of these 3 wings, we had decreasing settlements. And the differential settlements were roughly about half from settlement. And remember, this raft is 3.7 meters thick, but because it was so extensive, there was the potential for differential settlements. Now, this is a diagram showing on the vertical axis the settlement, and this is the distance along one of the wings. And these diagrams show settlement profiles measured at difference, the last one being at about 80% or so of dead load. Here is our prediction, or one of the predictions of the final profile, which we think would actually have overestimated the settlement, but we estimated, Hyder and ourselves, that the maximum settlement long-term would be in the order of 5 millimeters. And so our predictions were conservative, but really quite reasonable. And of course, here are pictures of the progress of 2006, 2007, and the grand opening in 2010. Now, here is another building now consulted to try and provide some information on the settlement of this really tall tower, Convention Centre. There's a large number of piles, 525, and the raft was quite thick, 4 metres thick, with local thickening in core. And the piles are of 3 different diameters and varying lengths. So we carried out a number of analyses. The first of these was we did a normal analysis where all the interactions were included. Then we did an analysis just to try and demonstrate the importance of including all the interactions. And then we did another analysis where we just used interactions whatsoever, but we did incorporate the piles and the raft. And this is the outcome, that if we take account of all the interactions, we will get kilometers. But if we totally ignore the interactions, then we would predict and seriously underpredict to be of the order of 20 millimeters, so only a quarter of the settlement that we believe is more realistic. This is the maximum rotation. The raft moments and the pile loads are not that much affected by interaction, but the settlements and the rotations are very much affected by interaction. This is now shows the effect of including the raft into the analysis. If we allow for the raft, then the maximum calculated settlement is about 82 millimeters, and the maximum 500. However, if we ignore the raft, then our calculated settlement is huge. Our is enormous. It's at 1 in 80. And also the maximum pile load is almost doubled as compared with the proper analysis. This exercise demonstrated was, firstly, that it was important to incorporate interaction, and secondly, how for the beneficial effects of the raft. Otherwise, you would have to use much piling deeper. The next tower is the Diamond Tower in Jeddah, and we were asked here to try bring a bit of light on the possible effects of cavities that were identified beneath this tower and looking at the potential for tilting of the tower. The geotechnical in Jeddah is not uncharacteristic of that. You have a lot of limestone, and there tend to be in places cavities, and so we have a deposit of limestone with random foundation details, and this was designed by others, 0.5 meter thick, 145 board piles, 1.5 meters in diameter, length piles, and we had this serviceability load of 2,850. This is the layout of the piles that we were provided with. And what we did here was we looked at the geotechnical and then set up a series of randomly generated cavities to try and mirror what was found in the ground investigations, and we modeled the size and location of the what we knew from the ground investigation. We then had initially values of the modularly modified in the light of some data that we obtained. And we then did a series of 3-dimensional finite element analyses, incorporating in each of these analyses, firstly, single cavities, idea was to see how significant those cavities were of the foundation system. And what we found was that there was an extra only 2 to 3 millimeters of settlement, millimeters maximum settlement. Multiple cavities, then the settlements could increase up to about 74 millimeters. But the other also important thing was that with random cavities, you now have a non-symmetrical settlement pattern system, and the loading is symmetrical. And so here's examples. You see the settlement contours are not exactly symmetrical. They're skewed a little bit, so you'll get a rotation effects of the cavities. And there is also an increase in the bending moments in the raft, but not a huge increase. So what we observed from these analyses was that cavities can cause some increases in settlement. A single cavity, a larger number of cavities, a bigger increase. The settlement pattern can be non-symmetrical, but the raft acts to reduce the impact of those cavities on sides, an additional measure of what we call redundancy. The next case is the Incheon Tower in South Korea, which we called Korean company, and this was to be the world's second tallest building, 600 meters tall. And we came up with a design that looked like this: a central core with 3 wings, 172 board piles, very large diameter, 2.5 meters long typically, but possibly longer, and a very thick 5.5 meter thick raft. The challenges here was that this was on reclaimed land, so it was going to have to be reclaimed. It was initially in the ground, in the sea. Geology, very tall building, and limited tolerance to differential settlements. So here is the site when we investigation, and here is a plot of the contours to bedrock, just showing that very variable in elevation. And what we had to do in the design was actually to develop 8 different soil then had under the footprint of the tower. Here is a typical one showing modulus for the ultimate skin friction and ultimate end bearing with the basis of the available data, both in situ and laboratory data. So here is the before, and we did a calculation of settlements using a very simple approach initially, using an equivalent in our initial assessment, 75 millimeters. We did the detailed design using the program GARP, and we got 67 millimeters. We did a final design finite element analysis where we took account of basement walls and of the contact of the raft with the soil, and got about 56 millimeters of settlement. And then the other thing that we looked at and the importance of including the flexibility of the raft, not rigid, because some of the software that we commonly use to design pile groups and pile rafts assumes that the raft, in the case, if we had assumed that the raft was rigid, would have a load of 24 meganewtons, and the corner piles would have a load of 85 meganewtons. If we allow for the flexibility of the raft, then the distribution of load is much more uniform. The stiffness of the piles is uniform, and the settlement of the piles, of course, you get a bigger settlement if you have a flexible raft. you don't have these huge axial loads that the rigid raft provides for you. Now, these are just some pictures, finite element analysis. These can be helpful in us understanding how the system works. This is after a combination of loads if you don't allow for basement contact and have no walls. And here is if you do have basement contact, and we found that the bending moment in the piles was reduced by 10 to 15%, and that of course is a saving in the reinforcement in the piles. Just very quickly, there was some for this, and it turned out that our design assumptions were actually rather conservative. And at the time that we were going to do a redesign, there was a halt put on this project, and that halt has not been lifted. As if it is, we will be able to refine the design of the foundation. Finally, let me just very briefly present some cases that were presented firstly by our colleagues in Mandolini, Vigiani, and Russo in Italy, and that case of twin towers in Naples that were designed with no allowance for the raft. And these towers were built with 637 piles in total. And what Mandolini and Vigiani and Russo found was that they got extremely good agreement between the calculated and which incorporated the raft and the distance along the slab. If they had the raft significantly greater. But the important thing was this, that when they reanalyzed that foundation system, they found that reducing the number of piles from 637 to 318 led to virtually no increase in settlement. The system has probably twice the number of piles that it really needed to have. So the computer is 318 piles compared with 30 millimeters for 637 piles. So those extra 319 piles, a 3 millimeter settlement reduction. And the differential settlements actually were less with the lesser number of piles. They could have used 12.7 kilometers less of piles, 6,000 less than piles. Would have been a saving of about 50%. Back has done studies found again that if you allow for the effect of the raft, rather than designing the system as a fully piled foundation, you can get substance. In this particular case, for the fact that it was designed as a piled raft, he estimated saved about 5.9 million. These pair of buildings, hopefully still standing in Kiev in Ukraine, the estimated saving $3 million US. So just finally, to conclude, the settlement as the number of piles increases, there is a major reduction in settlement for a relatively small number of piles, but increasing the number of piles beyond costly. Piles can also reduce the bending moments in the raft if you put them in the right sort of places. Differential settlements much more than total settlements. And the foundation performance in some cases can be improved by using shorter piles below lighter loads and longer piles below heavier loads. So just finally then, my final remarks can provide considerable foundation economy in the right circumstances. And importantly, in these days where sustainability is such an use it sustainability, using less concrete, using there's considerable experience of successful application of piled rafts, and I think we generally don't take account of in design is that you can increase the pile. In effect, you get something for nothing, and that is something that is quite rare. So that's the end of my talk. Thank you very much, and again, apologies for our technical issues. And just finally, I have a series of papers that fall if you wish to pursue this subject further. Some of these I've referred to in my talk.
Thank you, Professor Poulos, for this distinguished and informative talk about piled raft, and it is indeed fascinating to see this value engineering of this option reaching up in some cases more than 50%, which is really impressive. I can see there are already some questions. We will take them in the panel discussions after we finish all the talks. Now, I think we will head to Dr. Marwan, insights on savings in piles and sedimentary rock in Dubai. Dr. Marwan, the stage all is yours.
Hello. Yes, thank you, Hamzah, and as well as thank you, Professor Harry Poulos, for your informative presentation. I don't know if you can hear me, Hamzah.
Yes, we do.
Yes, can.
Okay. Yeah. And now I'm sorry, I'm sharing my screen. Yeah. Okay. You can see my screen as well.
Yes.
Okay. So let me just close the camera as well because of just to avoid any quality issues. Okay. So in this presentation, or actually very short presentation, I will speak about some researches or some investigations done in Dubai, in the United Arab Emirates, especially in Dubai Sedimentary Rock. And in this presentation, I will be talking about 6 researches or 6 publications was done which related to Dubai Sedimentary Rock. The first one, which we'll talk about the stiffness and strength of the sedimentary rock, which long time did it with Professor Katzenbach, and the empirical, friction to unconfined compressive strength correlation for evaluating capacity of weak rock in foundation. This was done with Dr. Sujata and Professor Harry Poulos and Professor Deepankar Chaudhary. And the other things also like value engineering done by Dr. Sugata, the second one, which is skin frictions done by Engineer Benoit and Engineer Rea, and some engineers here locally with Atkins. And those all the research is done, which shows a lot of room to reduce or to do some value engineering, which related to the sedimentary rock. So I will start with this one. So I will start with the research idea, and this is the agenda of the first part. So I will be talking about why this idea came and how we come. So usually when we do all the time here in Dubai Sedimentary Rock, we do the static load test. We do it in, and we found out there is a big difference between the calculated settlement using the empirical equations and a static load test. From that point, by collecting a lot of data related to that, we found out that we should investigate more about this problem. So we decided to go with this study objective, which we'll talk about evaluate, perform, investigate, develop, and provide. So first of all, we are evaluating our soil properties and geotechnical investigation report. And the second thing, we perform comparison between the pile calculated settlement and the empirical and we call it conventional approaches, and the numerical modeling with the FEM and the static load test, and investigate then how the single pile performs in the weak rock or the Dubai sedimentary rock, and evaluate the Young modulus or modulus of elasticity of the rock. Then we develop a comprehensive methodology for the analysis of the designing of the single pile embedded in the weak rock. Then provide a contribution to the geotechnical engineers, especially with regards to providing economical design, foundation design, and green construction. So simply we start with these 3 steps, and we believe that there is underestimating for the soil properties with respect to the Dubai sedimentary rock, and there is a kind of over-designing, and we believe that we should do a kind of optimization for our design. So that project, basically we have 28 plots, more than 40 towers, and we have as well 116 static load tests and 196 boreholes. So this is the location here in Dubai, and those are the plots which we have it in Business Bay and Dubai downtown, which is not far away from Burj Khalifa, were designed by Professor Poulos, the foundation. And this is exactly what we found out. This is the soil profile. We have in the top 5 to 8 meters, we have sand. After that, we have Dubai sandstone and Dubai siltstone. And we, in this research, we have 195 boreholes, and we have almost like 37, we have it more than 60-meter depth. So this is the soil profiling, and this is one of the pile which we investigated. And you can find out here exactly what is the soil profiling. All the tests, all the pile tested, all 116 are in the rock because of the basement, so the foundation is overlying on Dubai sedimentary rock. So basically here you can see this is the settlement calculation. We had mainly 3 main references which we rely on: the settlement, Baraja MDAS reference, and Bowles and Tomlinson. Then we decide to use Blacksys as a software, and we have the static load test. So here, when we did the calculation of the settlement, we did it based on E, which provided in the geotechnical investigation report or the soil report. And here you can see those settlement, and here also the Blacksys, the last one. But you can see here the big difference between the static load test and what the settlement calculated based on the E. So based on E, modulus of elasticity provided in the soil report. So from that point, we decided to move on and to do a kind of back analysis. And step 2, we did the back analysis by trying to fit the curve of the FEM model and back calculated value to find the value of E. So simply we decide to do that. So here the FEM based on the soil report, and here the static load test, and here when we applied, and you can see it's fitted 100%, and here you can see the E value which calculated. So previously we used 60 meganewton, and simply when we back calculate those values, it was reaching 5,000. So 83 times the E value provided in the soil report. Then we decided, okay, let us use our what we call it new E in step 3, and we decided to use it in our also empirical equation to evaluate and to make sure that what is fitting 100% or not. But the problem is still we have a gap between the empirical approach that DAS and Tomlinson and Bowles, and settlement back calculated by Blacksys, and settlement from the static load test, and we are using the same E modified. So we investigate more. We found out, as you know, the settlement calculated using the empirical approach is divided to 3 types of settlement. S1, which is settlement due to the elastic shortening. So usually when we use the elastic shortening, we use the the full length of pile. So we decided to go back to Blacks's and see what is the effective length or the length of pile which is affected by load. So simply we found that the effective length or the affected part of pile is 11 meter when we apply 150 times the working load, and when we applied 100% of the working load, it's only 9 piles. So when we correct the value of L in that equation, we found out the following. We found it's simply everything is matching 100%. So even though in our empirical approach, we don't have that much problems, the only things we have to take care about it, the value of E. And when we calculate the settlement due to the elastic shortening, we should calculate exactly the length which is affected by the load. Then we did a small comparison just to make sure that between the Blacks's and GTS and Maida's GTS, and we found they are matching 100%. So now the summary of the 116 piles. This is, you can see the E value provided in the geotechnical investigation report. You can see we have almost between 40 to 60, and the maximum we had it 201 or 220 MPa. Most of the geotechnical investigation labs or geotechnical investigation reports relying on these equations, which provided in Tomlinson, which E is equal to J multiplied by MR QUC. And as we know, the mass factor is relying on the RQD. That means there is a kind of human effect to that part. And then you can see the second one related to the MR related to the soil classification, and the UCS at the end is a laboratory test. Now the values which we found it when we did the back calculation, you can see what we found. We found the minimum value almost closer to 900 MPa or 1000 MPa, and the maximum will reach up to 20,000 MPa, which is a huge difference related to that, related to what we call it, the Dubai Sedimentary Rock, the stiffness of Dubai Sedimentary Rock. We took as a case study, we have those 4 towers in Dubai, we call them Paramount Towers, and in that test, we have, in that tower, we have 5 static load tests, and you can see in all of them when we did the back calculation. So the previous one, the previous pile, which is 60, the back calculated value of E was 5,000. The second pile was 60 as well, which back calculated value was 3,000, which is almost 50 times. The third one was 4,250, and the minimum value was back calculated 1,450. We decided to do a kind of, because we measured the settlement of the building and we tried to back calculate it by rule of thumbs, and we found out the E value for the whole building is very close to 1,540. Simply when we go to this case study, so the minimum E value calculated was 1,400, which is 25 times more than the values which provided in the geotechnical investigation report. And then in this project, we have almost 618 piles, and the length of those piles, when we calculate them, is 20 kilometers, which is 1.2 with 1.2 dia. So simply the total pile volume is equal to 22,000. And this one, simply we can save 10 kilometers of this length if we use the proper E while we designing the pile. And the conclusion we will go for of this case study for we should take care about calculating the E value, relying on the empirical approach. Try to move to something like the wave shear velocity or pressure meter, or to get higher values. Back calculations for the sedimentary rock is giving a factor 20 times E value. Using effective length is very important to calculate settlement, the exact settlement using the empirical approach. Then the numerical techniques are an accurate estimation based on the research we did it to calculate the E value, and you can see that it is the minimum value for our case study was 1,400 MPa. The settlement recorded for the whole building was 15 millimeter for the structural skeleton only. And now, based on that research, we can say major saving could be done if we just invest more time and we try to do our design more accurate by using the back calculation things. Also, I want to highlight few researches, as I mentioned, the review of piling industry practice in Dubai, which is done by Benoit, Andrea, Michelle, myself, and Mr. Joshua. And also the value engineering, which is done by Dr. Sugata and Professor Dipankar and myself, and as well as the value engineering of Paris Foundation for Tall Building in the Middle East, also so Dr. Sugata, Dipankar, and Akash Parma. And this is the last research was done by between Dr. Sujata and Professor Dipankar and Professor Harry Poulos and myself. The conclusion of that you can see here is a quick summary about that, which showing that the values of friction, which is alpha beta, could be used even some up to 0.42 or 0.54. And you can see also the barrettes could help in length reduction by 11% was achieved. Also, we did a lateral analysis for the pile, and again, that's a research was done with Dr. Omar in Abu Dhabi University and myself, and as well as Dr. Ramesh and Akash. And we found out also in the lateral analysis, we have the brooms method here is you can, which a lot of contractors and consultants using it to do the analysis of pile. You can see how it is really giving a huge conservative approach to calculate, for example, the lateral load capacity or the deflection of the pile itself. We found out in using the 3D finite element with hardening soil for sand for the top layers is helping in that direction. So this is the links for the paper, which will be shared by Engineer Hamzah, and thank you all for listening. Now we will allow Hamzah to present. Hamzah.
Thank you, Dr. Marwan, for this interesting cases you have shown, and it was impressive to see also another value engineering and 10 kilometer saving of piles, which indeed call for further efforts from us as engineers to go far away from the over-conservatism in the field of foundation.
Yeah. Thank you, Hamzah. Now we will allow Hamzah to present a case study, which is, if you share the screen, Hamzah, yes. Hamzah, he will share a case study for the largest micropile project was done in Bahrain. Hamzah, he's a geotechnical designer and as well as an academician. He's teaching as well in Bahrain University as a part-time, trying all the time to connect between the academia and the practice and the industry. He has a 10 years experience of geotechnical designing. He is a very active engineer. He graduated from University of Khartoum, and he did his master in Saudi Arabia in KFU PM University. He's the founder of the Geotechnical Engineering in GCC. He's active trying to do a lot of activities related to that. So Hamzah, you can take care. You can take the microphone and you can start presenting the case study.
Thank you, Dr. Marwan, for this great introduction, and welcome everyone to this small case study, I would say it. So since we talked about piled raft with the father of piled raft, Professor Poulos, now let's talk about the baby, Micropiled Raft Foundation, and We'll show you a couple of cases, one in Bahrain, as Dr. Marwan mentioned, and also one we have done recently in Saudi Arabia. So the project of interest I wanted to show you is claimed to be the world's largest micropiled rafts, which was completed. The skeleton approximately was completed in 2020 in 22 in Bahrain. The project was featured also and nominated in the Year in Infrastructure Bentley 2021. So the site is located on a reclaimed island in Bahrain on top of a shallow artesian aquifer. It is a public housing development project with a total built-up area for the foundation of 70,000 square meters, with buildings floors ranging from 8 to 22 floors approximately. The challenges was there. It is a reclaimed island, consists of reclaimed soils, loose to medium dense usually, with large spans between the column, massive loadings due to the large spans, and as we mentioned, weak soil and shallow aquifer that needs to be protected because it's a national preservance for the Kingdom of Bahrain, and also there is a need to reduce the carbon emission and the cost budget and aspects as well in the project, because it's being built in a newly developed islands. So all the aspects of the green building and green construction needs to be considered. So as a value engineered solution, there are several years of discussions and evaluation done between all the teams involved in this project. Myself was involved approximately 5 years till the realization of this project, but I think other people in the team have been longer looking at this project. I think more than 8 or 9 years, as I will mention later. But at the end, compared between different options like rigid inclusions, deep soil mixing, port piles, raft alone, and many other foundation solutions and ground improvement solutions, the project has been done with micropiled post-tension raft foundation. The micropile, if you see a lot of these, it's displacement driven ductile iron micropiles. So it has been selected, as I mentioned, against different options of piles. As a result, there was 70,000 square meters of post-tension rafts supported by 12,000 shallow micropiles with total length of 90 kilometers. It was designed and optimized using calibrated 3D finite element model with soil structural interaction, coupled actually between the structural and geotechnical model. The micropiles were fast to install. We were able to achieve 65 piles with the subcontractor of the piles and 490 meters per day of installation for the piles, which deemed to be quite fast. And also we had the least disturbance on the aquifer with this proposed foundation system. The raft's thickness and differential settlements were reduced further by the post-tensioning, as Professor Poulos mentioned, that the differential settlement in some cases would govern. Applying BT will further help also to control this. We have an extensive geotechnical investigation program, including also 120 micropile load tests and settlement monitoring devices installed within the raft foundation. As a result, this solution was showing savings in carbon footprint and greenhouse gas emissions by at least 76% compared to other conventional solutions. The load sharing of micropiles after the evaluation of the calibrated model are expected to be between 65% to 70%. These are typical building from the project. These are some of the references we have used and adopted: the Federal Highway recommendations on filings and PTI publications on the post-tensioning foundation elements. We have done also parametric study and sensitivity analysis using different techniques. One of them is the artificial intelligence, artificial neural network, as you can see here, but also we have used different methods like the support vector machine, which provided the most accurate result. We have evaluated also here in the charts on the right, parametric study to decide the optimum number of the micropiles. As Professor Poulos showed, that there is an optimum number of piles. No matter how many piles you increase after that number, the reduction in the displacement or the settlement will be minimal. Sorry. And also we have done parametric study on the mesh, the numerical mesh in the model. We can decide the optimum size of the mesh, which has the least impact on the results. This is one example for, I think, the classification and regression tree method for the sensitivity analysis we have run. We identified that the mesh, the numerical mesh, has profound effect or impact on the results, which is of no surprise. And also the BREF, because we have used the hardening soil model with small strain stiffness model for the soil. The BREF has also the second largest impact, the over-consolidation ratio, and then E50. Those are the top 4 impactful parameters. We have used, if you can see on the chart, it is the micropile load tests conducted on site, and we have calibrated the numerical model based on these results. The green and the solid green and brown or red curves are from the sites, and the dashed one is from Plaxis after the back calculation or calibration of the model. And however, this has been done manually, the back calculation or the calculation of the model, but it took more than 1 week to achieve this matching. However, I have, with another colleague of mine, worked on an optimization tool to shorten that time. We'll show it in a minute. These are one of the two of the tallest buildings with approximately 22 floors height. And you can see the displacement. The maximum displacement was approximately 30 millimeter, and those black dots or points represents the instrumentation we have placed within the Raft Foundation. With us, I think also today, Engineer Mustafa Jamal. He's the head of structural department at Gulf House Engineering. He has extensive experience in structural engineering in Bahrain, and he was also the consultant for this project. I believe he has been looking over that project for more than 13 years, if I'm not mistaken. And it took really great efforts and team efforts from everyone involved to realize such a project. The other project we have done also recently with my current employer, Geofem, in Saudi Arabia. It was challenging ground conditions with problematic soils and sabkha and creep. And the interesting part here, there was an existing port piles, and we have proposed again Micropiled Raft Foundation to support the building. And we have developed our in-house micropiles software to check the capacity of the micropiles and the buckling. But what is also interesting, we have used remote sensing in SAR satellite monitoring and historical retrospective analysis for the site. And we calibrated the creep model in Plaxis with the INSAR value, as you can see in the chart here on the bottom left. As I mentioned, that it took us more than 1 week to calibrate and back calculate the numerical model with pilot tests. So I have worked jointly with Dr. Alaa Kurdi from LOSIS, UK. He is a senior geotechnical consultant, and we developed an automated and optimization algorithm tool to calibrate Plaxis 3D models using the micropilot test. So we have taken a case study for a micropilot test for a project in the Gulf region. We have used Plaxis 3D and Mohr column model, but we can extend this work for any other constitutive model. We have an initial values estimated from the soil reports, because this is our starting point. As Dr. Marwan said, we always start from the soil reports. We estimated a cohesion of 4 kilopascal, friction angle of 35 degrees, and elastic modulus of 5 megapascal. We have developed the automated method and optimization algorithm after different trials, and the total duration we started by a method that requires 5 hours to come up with the optimum solution, and we ended up to the most optimum method, which requires few minutes, I believe less than 30 minutes even. We have achieved an optimum values that provide us a pleasant match between the site and the numerical model, with cohesion unchanged, 4 kilopascal, friction angle increased to 43.7 degrees, and elastic modulus of 33.8 megapascal, which is again huge increment in the elastic modulus, and it's of no surprise after seeing what Professor Poulos has shown, and also Dr. Marwan, that always or most of the time the elastic modulus and the stiffness, the actual stiffness, is much more than what is presented in soil reports. Initially, it is underestimated in the reports. Also, we are currently working as a next stage. We have already some initial results, but working on that further on the automation and optimization for piled and micropiled rafts in terms of number of micropiles and locations, also using automated and optimization algorithms, because as Professor Poulos mentioned, that putting the piles, or in this case, the micropiles, in the right location, it will have a significant impact on the reduction of the moment and its placement. This is an output from the optimization algorithm we have developed. You can see that every point represents a model, and this is not a convergence curve. This is just all the iterations we have done. On the y-axis, you can see the sum of square errors. And we keep changing the cohesion, friction, and elastic modulus till we decide what is the minimum errors and the most optimum option. And here you can see the optimum solution. The solid black line represents the initial estimated curve from Plaxis 3D based on the parameters from the soil reports. It's very far from the red dotted points, which represents the field pilot test. And after the optimization, we have reached to this dashed black line after the optimization from Plaxis 3D with R square of 0.9987 between the two. And thank you. You kept it short. And if anyone interested to know more about the optimization tool or use it, maybe for your project, feel free to reach out to me anytime. Now I think we will take the question and answer. Professor Poulos, if you can also unmute yourself and get your camera, as well, Dr. Marwan. I can see a lot of questions, but first to start off and break the ice, for the panel discussion, maybe we can start with the three main questions to direct the panel discussions. We'll start with Professor Poulos. Professor Poulos, if you can provide an insight on the fundamental difference between piled rafts and rafts on piles.
Look, I guess I don't know whether there really is a difference, but piled rafts to me are situations where you have a piled foundation and you take advantage of the effect of the raft in reducing the number of piles. The other way around, and I think I said to it, it's an alternative view, is that the piles add to the raft so that you add a distinct number of piles so that you improve, you're really using an enhanced raft using the piles so that you put a relatively small number of piles where they will do the most good. And these two things, I mean, you wouldn't use the second option for a tall building, but you may use it for a large factory, for example, where you've got a weak area somewhere, you've got a big slab and then there's a softer area. Maybe you put in a number of piles to stiffen up the raft where the ground is not that good. And so there, I mean, the issue is you don't worry too much if the piles are actually fully mobilized, because what they're doing is providing you with a negative load, if you like. And if you ask an engineer, would you like a means of reducing the column load? He would or she would say yes. And then you say, well, how about I put a pile under there? And even if it generates its full capacity, you still have the column load less the capacity of the pile as a net load on the raft. So there is, I guess, a psychological difference and also a physical difference between the application of those two concepts of piled rafts and rafts with piles.
Thank you, Professor Poulos. And also the other question arises, do we need a code for piled rafts, or we can just follow the guidelines and the engineering judgment?
Right. In Australia, we have a code, but piled rafts are included in the code, but much is left to the judgment of the engineer. I think we have to be very careful in codes that we don't sort of have what we call a cookbook, so that people do things without thinking. And the whole idea, I think, of designing piled rafts in particular, but any foundation, is that you need to think about what you're doing rather than, and I hope there's not too many structural engineers on the line, but some of the structural engineering codes just require you to do certain calculations and you don't necessarily think why you're doing them. With a geotechnical code, and that's why I would favour, if you do have it in a code, outlining principles, but not specifically how you then execute those principles.
Amazing answer, and unfortunately we are keep facing such an issues and challenges when we have been asked for codes. I think also Dr. Marwan maybe can add on this based on his experience, much frequent.
It's a very good question, to be honest, from even my where I work and I review the problem, we will start a little bit with the codes, and it's really sometimes difficult to judge in this case. But I agree with Professor Poulos, this is relying on the engineering judgment, and the engineer, what he's deciding depend on the case, depend on the type of soil, the situation. Reclaimed land is totally different when you have very stiff rock, or we have a device sedimentary rock. So I'm totally agree, and I think slowly code will be updated and will accommodate those type of advanced design which related to the foundation.
Thank you, Marwan. Another question also for Dr. Poulos. What do you recommend when it comes to the safety factor for pile? Is it like the conventional safety factor for pile foundation, pile draft?
Look, I think, again, it depends on the circumstances. With tall buildings, and again, particularly an additional measure of safety. Okay, so the piles themselves, I'm quite happy to design those with a factor of safety of 2 or even a little bit less. Foundation, then you probably need to go a bit more because the piles are all you have. The other circumstance factor is offshore, because if you have a factor of safety of 3, for example, offshore, then the piles become enormous and just you or design them. But normally, I think as long as you have a safety factor of 2 and you've got the raft, which provides you with an additional safety factor, as I said before, you will find that it's a technical issue, and I think you found that in the cases, gentlemen, where you talked about, it's the settlement that controls the design rather than the overall capacity. It's just one thing I will say, and that is that there is a tendency now, particularly in tall buildings, which obviously I think we're all interested in, high aspect ratios, where you have buildings that are 20 or more times taller than the size of the footprint. And that means that you have large overturning moments on a small area. And there you would have to be very careful about you applied, not so much because of the vertical loading as such, but because of the overturning moments and the push-pull effect on the small footprint.
Interesting and informative, detailed answers, or also another frequent questions being asked about the pile draft. Finally, before we move to the panel,
just if you,
yes,
if you,
yes, please.
if you allow me regarding the safety factor, Euro Code 7 now giving a lot of room when you do testing, when you when you increase the number of PTP testing, for sure allowing you to reduce the safety factor. So when you investigate more in the ground and you investigate more and do more testing, for sure you can go in that direction. But I don't support going in this direction without doing a proper or additional testing. So I'm totally support the approach of Euro Code 7 in this case. Yeah.
Yes, and that's what happens when the more benefit you get, and effectively the lower factor of safety you can adopt.
Interesting. So the final question before we move on to the audience questions will be what we are still missing in the pile draft design and construction, or what are the future developments in this field?
Oh, that's a question. I mean, in principle, I think we now have tools that, well, analytical to analyze the most complex situation. And I mean, some of the analyses that you've shown, some things that we couldn't do 20 years ago. But I think there still remains the major issue of ground characterization. And I think you've touched upon this, Dr. Marwan, and yourself also, that this, in my estimation, is not being able to properly classify the ground, and perhaps trying to, in some ways, overcomplicate the problem in one way, but oversimplify it by not allowing for what might be geological imperfections in the ground. And this is why I think I was interested to see your use of satellite measurements, because I think that's a future development, and it's something that should be put into a code. It is that you should be forced to make settlement measurements, and I think in Germany that's the case, that is something that will spread, because this can catch problems at a much earlier stage than when they actually appear. Too late to do anything about them.
Oh, thank you, Professor Poulos. Dr. Marwan, if you want to add anything before moving to the audience questions.
No, I think we should give time for audience as well
For the
to
audience,
ask.
yeah. Sure.
Yeah, please.
So we'll start with the first question. It's from Amir Alipour. He asked, when it comes to the simplified methods, not the finite element of the advanced analysis, is there any recommendations or considerations to be taken when it comes to calculating the soil elastic modulus? How they should
yes.
calculate it?
Yes, a very good question. And I think both of you touched on that important issue. We need to be very careful when we're doing that we don't go back to textbooks. And I'm not trying to sort of denigrate textbooks, but modulus might have been obtained from footing tests or something. Those sorts of values may be totally inappropriate for pile foundations. And as you said, under seriously some of the older sort of information, and that I like using geophysics and getting shear wave velocity small strain module. Found that and others have found in addition in working in the Middle East, that if you take the small strain modulus and then reduce it by a factor of 5, so you take 20% of the small strain modulus, you're getting somewhere close to a relevant sort of value. That's a key issue. And what I like is that you are in control. You have to exercise your judgment. And I think this, if we go back to some of the legends of our discipline, like Peck and Skempton and so on, they didn't have finite elements, but they saw what was injected, and they modeled those in a simple way, but they actually encapsulated the critical issues that molecular problem. And in the same way, when you do simple analyses, I approach very frequently to analyze a piled group or a piled raft, because that gives me impression as to whether my settlement is 5, 50, or 200 millimeters. And you can go from there. But that all depends on how you model it and, importantly, modulus values you use. And if you don't use the right sort of modulus values, you're wasting your 3D finite analysis, because, as you know, garbage in, garbage out.
Exactly, and thank you, Professor Poulos. Another question, I think it might be arised from a student, I guess, Khalid Al-Dosri. He's asking, what are the main differences between piles foundation and piled raft? It might be something new for them, Professor Poulos, if you can give them insights.
I mean, in a pile foundation, you design the foundation take 100% of the load, okay? And you almost always have a slab, but you assume that all it does is it just sort of supports the column. In a piled raft, we make a conscious effort to allow some of that load to be carried by the raft. And our success in put the piles, how many piles we have, and what their characteristics are. And so potentially you are able to number of piles in a piled raft compared with a full pile foundation. Sometimes we can only reduce them, the number of piles, by 5 or 10%, but that's still less carbon, and so it's worthwhile.
Thank you, Professor. Another question also from, again, Amir Alipur. He's asking, can we use pile group reduction factors for a group of piles that contain different length and diameters?
That's an excellent question. And again, here is where you have, because if you're going to do that, you have to try and model that complex pile group as an equivalent simpler pile group with all the piles the same. And so you might want to take an average sort of length of the piles if they're different length, and an average diameter or stiffness. But yes, judgment comes in. And this is why I love our subject so much, that it allows specs as your experience and ability. And this is really, I would urge younger to sort of interact with older engineers and to get their ideas on how you can simplify a complex problem so that you can analyze something that is simple but still, I mean, that's the real hallmark of an engineer, is to be able to do that.
Thank you, Professor Poulos. Another question also from Siham Fathi. She's asking, it seems that a case study for her, and she's asking that she tried the different load combinations of seismic and wind loads along with the vertical loads, but when they used different combinations of the lateral loads, there was no impact on the load sharing on the piled raft. Well, is that the case, or compared to some case studies you have worked on before? Or
yes, look, if you are doing a fairly simplified analysis of the piled raft where you're only focusing on vertical loads, then perhaps the moment component, which you might be able to incorporate, that may have relatively little effect on the load sharing. If you do a more do this towards the end of the project when we're in really detailed design and we might be using three-dimensional finite elements, there you can take account not only vertically but laterally, have a better idea of what the raft does for you. And I think, as I indicated before, my experience is that the fact that the raft is in contact with the ground and perhaps embedded into the ground can have a very important effect in the and to a certain extent the moments, as compared with the case where you don't take account of the raft itself. And so again, that's something that reduces the design requirements without having a bad effect on the stability.
Thank you, Professor. Another question, also I think from a student, if I'm not mistaken, if the differential settlement was still a concern in Piled Raft Foundation, what further measures can be taken in that case?
Yeah. Again, good. I think have the option in that case of trying to modify the settlement profile by doing one of two things. We try and make the area under the part that is settling more stiffer. So we put in more piles, longer piles, larger, and we try and even out the settlement that way. Or alternatively, and this is worth thinking about, we try and reduce or increase, part of the foundation that isn't settling as much. So we can actually, in some cases, we can think about removing piles or reducing the length of the piles. So you don't always have to make the thing stiffer and stiffer. You know, you're either by reducing the maximum settlement or increasing the minimum settlement. And again, this is engineering. You know, you have options that you can follow. And this, we have done this, and I think if Dr. Marwan will know this from Professor Katzenbach, that's what they did with the mesotherm, that they had piles that were short on the inside so that tended to even the differential settlements out, and you got a much smaller differential settlement. That's engineering.
Interesting. Thank you, Professor Poulos. Another question also, I think, from students again. They are asking what are the differences between rigid and flexible rafts, because I think you have shown differences in settlement when we consider the raft as rigid or as flexible.
Yes, absolutely. Good question. If you have a relatively small foundation area, then a 1 meter thick raft or pile cap is quite rigid. But if you have, like in the Burj Khalifa, you got tip to tip meters, 3 meters or so, 3.7 meters is still flexible, and it all depends on to the size, the area of the raft. Okay, if you have a very small thickness to size, are actually going to be relatively flexible. And what happens then is that you will get a differential settlement, okay? Even though the raft may be in real terms meters thick in one case but we still had calculated differential settlements of 10 to 15 millimeters because of the size of the raft. But what I was trying to point out before was some of my original software allows you to assume a rigid raft, which is fine for a small area. Building, you can get deceptive results where the loads on the outer piles are very high and the loads on the inner piles are very low. And that's not realistic because you cannot get a really rigid raft, a very wide building. You would need a raft, I think I worked it out once, about 25 to 30 meters thick to have something that is really rigid. For solution, I don't think we need that sort of thing in reality. We can't build it.
Thank you, Professor Poulos. It is interesting indeed because there are some books provide some methods to differentiate between flexible rafts and rigid rafts, but there are huge gap in between that. They are in between flexible and rigid. They are neither rigid nor flexible.
Yes,
it is indeed.
And that's the characteristic of piled rafts. You're almost always in between with the piled raft.
Awesome. Again, there is a question from Siham Fatih. She's asking, is there a range for the undrained stiffness for soft clay and medium clay soil? Because it was not described in Terzaghi.
Look, you ask 20 different engineers and you'll get 20 different answers. Soft clay, I mean, is up to about 25 kilopascals. The medium may be 50 to 75. Stiff is 100 plus, and very stiff is 200 plus. But look, in my head, I don't even look. But, you know, if somebody tells me I have an undrained shear strength of 15 kPa, that's soft. If they tell me it's 200, it's stiff. So I don't think you can define these things. You really need to measure them. You know, if you're going to do any detailed design.
Thank you, Professor Poulos. Another question from George. He's asking that you have mentioned, Professor Poulos, that the number of piles in the pile raft system will be reduced compared to the original design. But what about the raft itself? Does it increase in thickness, or does it lead to total net saving for the project?
Yes, and again, that's a good question. It really depends on the design of the piled raft. And as I mentioned before, couple of times. If you are able to locate the piles in the right sort of position, so under columns, so that you don't have a pile with nothing. So you try and put the piles where you're going to have columns or loads, then that I think can be beneficial in terms of the design of the raft. Answer the question, to be honest with you, because obviously we try and minimize the thickness of the raft so that we satisfy both differential settlement. So again, it will really depend on the refinement of the design so that you minimize the required thickness of the raft to satisfy primarily the rocks, okay? Because punching shear is a very significant mechanism in structural design. And so punching shear you can have if you've got a swim, you can have punching shear upwards if you've got a pile with two columns. I've got then a negative and two positives, and you get horrendous bending moments there and shears. So it's really a question of doing an intelligent geotechnical design.
Interesting. Thank you, Professor Poulos. Another question from Dr. Namli. He's asking, I think he's referring to the floating piled raft, and he's asking about what is the liquefaction resistance of non-end bearing piles while making shorter piles. Can it be more risky at sandy soil prone to liquefaction?
Yeah, that's a good question, and I'm not sure I can answer it properly. I mean, if you've got floating piles, whether it's a piles or a piled raft, obviously lateral movement, but I think you also have increased bending moments because of the fact that the ground moves differentially backwards and forwards. Yeah, look, if you've got no doubt that if you get liquefaction in the total profile, that you still have a chance of survival. But I think generally, with a lot of pile foundations, the liquefiable layers are confined to the top 20 or so meters. If you get sands lower than that, it's unlikely that they'll liquefy. So as long as you don't actually found the foundation system entirely within the liquefiable layers, I think your main design issue there may well be the kinematic bending moments that are caused by the fact that the liquefying soil is going past and the piles are staying rigid, so you get enormous bending moments at the interface between the liquefied and non-liquefied soils. And that's a very important design issue for seismic area. Certainly we've had to look at, even in non-seismic areas. I mean, we looked at that with the Burj Khalifa and the Emirates. The risks were very low because you don't have liquefiable layers, but it's still something that you have to have a look at. Yeah. So don't found them entirely in liquefiable layers, otherwise it disappears. But if you go down below, then you have a reason that the foundation system will be able to withstand the effects of liquefaction.
Thank you, Professor Poulos. Another question from Cheryl to actually Dr. Marwan. He's asking, the general pile load test percentage is approximately to 1.5 or 2 times only. So they said the piles often have higher load carrying capacity than this factors or percentiles. Does your back analysis account for this? I think he's asking about the extrapolation of the capacity. We also seek your recommendation on optimal pile load test loading criteria.
Yeah, in the case study, so we counted also for 150%. So the back analysis taken in account the working load and the additional load as well to 150. In few cases also we had PTP pile which reaching up to 200 or 250, and also we calculate that value, and we are considering in our account, but at the end we should take care about the curve, and we should be as you know, the static load test will have 10%, then 15, 25, whatever. In all steps, we make sure that the E value calculated, it's the settlement found it out from the back calculation is lesser than all the steps. So all the E provided in my research with Professor Katzenbach was we consider all the steps and we consider it up to 150% of the working load. Yeah.
Thank you, Dr. Marwan. Professor Poulos, if you want to add anything on that.
Is that with the Burj Khalifa, we actually loaded some of the piles up to 3 times working load, and they didn't. Yeah. They weren't near failure. So that I think just is reinforcing Dr. Marwan's position. The only other thing I would say is that now with Osterberg cell testing being more frequently used, we have the ability to actually load piles right up to failure, something that we couldn't do because the Burj Khalifa we could only put on, I think, 6,000 tons with top loading before you know, we reached the limit of the reaction system. So the Osterberg cell testing facility now enables us to put enormous loads on. You may be aware of the fact that with the Dubai Creek Tower project, which is unfortunately currently on ice, that they put a load of 360 meganewtons, I think, the equivalent on a single barrette. And that's for a single element. So we have the ability now to get much more detailed information on the actual ultimate capacity of piles, big section piles, than we did with top loading.
Interesting, thank you both. And again, a question I think for Professor Poulos from Dr. Mohammed Ajmal. He's asking how we can cater for the bunching effects from the pile on raft and pile draft system if the pile is resting on incompressible soil.
Yeah, well, again, I think it comes down to a structure issue. I mean, there will be some compression of the pile. You can't have a pile that doesn't move at all. But I think if you have a punching shear problem, then the normal structural solution is to do local stiff, and that's where you have high loads, shear loads, or punching loads. Then you just have to locally stiffen up the raft, and that's about the only solution that I think works. So it can be done. It can be done.
Thank you, Professor Poulos. Another question from Savi. She is asking that I think for Professor Poulos, we can optimize the pile layout and the pile by opting for pile draft system, but how we can verify the pile draft capacity?
Yeah, good question. I mean, the only means we have to verify it are firstly to do the calculations. Secondly, okay, but what you can do is that you can, as the pile draft is being constructed and then the structure on top of it, if you take settlement measurements and if you find that the load settlement characteristic is in agreement with your predictions, then things are okay and that your design is right. And I mean, that's the only way you can do it, because you cannot obviously load a foundation up to failure. So you have to do the best calculations you can, and then you have to take measurements to compare what is happening with what's happening, okay? And if there's a vast disagreement between those two, that's when you stop and you have to investigate why that is. And we've done that. I mean, I've been involved with buildings in larger than they should have been, and we've stopped, and we've actually then introduced additional stiffness elements into the foundation system locally to get the system back up performing as the design indicated.
Thank you, Professor Poulos. I'm sure there are so many other questions from the audience. Maybe we can get back to you later. One more last question we will take. What about the arching effects and how to count for this phenomenon in piled raft? From Mohammed Al-Sherbini.
Look, I mean, arching effects involve a distribution of stress from one element to another. And in a sense, a piled raft causes that soil by transferring some of the load through the soil to the piles. And so if you do a detailed analysis, what you will find is that under working loads, the top part of the pile actually doesn't take very much at all because of it's almost like a negative friction phenomenon that the raft is going down, and so the top part of the pile is actually sort of not taking much load, but it's spread further down into the pile. And that's something that you will find out if and when you do a very detailed analysis of your file. You'll find out exactly how that system works. Now, once the whole system approaches failure, then that arching goes, because once the piles fail, then they start moving. Sort of follows it down. But the arching phenomenon is something that is real and does occur in piled rafts, but generally under sort of working load conditions, okay? And it's not something that is necessarily something we have to worry about. It's just part of the system.
Thank you, Professor Poulos, Dr. Marwan, for this informative panel discussion. I think last there is Mam Bowie from, if I'm not mistaken, from GTC Lab in Dubai. He wants to share some lab measurements using advanced lab testing for sedimentary rock young modulus in Dubai. Maybe that can supplement Dr. Marwan's findings.
Yeah.
Thank you very much, the panel, for allowing me a few minutes today. Thank you very much, Professor Harry Poulos, Dr. Marwan, Mr. Hamzah, for wonderful presentation. From the presentation, I learned that we should have a dry approach for design and also a dry soil parameter for the design for get economical and reliable foundation. We here in Dubai, we set up advanced laboratory tests. We have measured some of the stiffness of Dubai soft rock using advanced lab testing, including local strength measurement and resonance column and bender element. I would like to show just one example in the test we done for a business bay in Dubai. The rock is consistent tight, as shown in the photo here, and the depth of the rock is about 33 meters, and the effective stress we apply is 330 kilopascal. And we use both the test include local trend measurements and bender elements. This is the results of the test result. The sample failed very early at about 0.25%. And the rock cannot fail, yes, because it exceeds the loading capacity of our load cell. You can see it roughly about 4,500 kilopascal. And then here the key point here I want to share is the young modulus at a function of shear strength, measure from at very low at 0.001%. The dark line is the one measure using local strength, and the red line is for external strength. You can see the difference between the two is about 3 times. And the stiffness at about 0.1% here. For rock is about 1,200 megapascal. And it's much higher than the value that we use in design for Dubai Foundation. It's about more than 10 times. So that is somewhat coincide with the presentation of Dr. Marwan. It's very interesting thing. And of course, for the external strength, for the standard stats, we also get about the stiffness about 500, just to 5 times more than the value we use. So it is so that how important we use advanced lab testing for design. Just a little bit the investment now, but save you might be up to like the presentation of Professor Poulos about $3 million. And of course, for using we can also use bender element, and the shear wave velocity measure here about 800 meters per second. And with 800 meters per second, we can work down the small trends shear modulus about 1,600 meters per megapascal. And with the Poulos, so the Poisson ratio of 0 or 0.5, you can multiple the shear modulus who put 2 or 3, you can get the young modulus about 3,000 or about 4,000 megapascal. So yeah, in the side, of course, you can use geophysics survey to get the young modulus, and from that you can get the stiffness, and then or you can use also the advanced lab testing here. So that one of the advantage of advanced lab testing here, because sometimes in the field, the interpretation of the shear wave velocity sometimes tricky. You're not sure the profile maybe on the left or maybe on the right or a little bit further. So, but with the dry lab measurement, you can anchor the result. So you can get the rise, just some few value along the profile. You can get the whole profile of the soil stiffness. Thank you. Thank you for your listening.
Thank you, my boy.
Thank you, Dr. Tan. Thank you. And just we'll add something to Dr. Tan. This is, what we mean when you do the advanced testing, do back calculation, try to rely on BTP, reducing the safety factor of as per Euro 7. All these tools together for sure will help to more economical design and will be more helpful to design a proper foundation or the proper design, which will be leading for sure to a value engineering for sure. Yeah. Thank you, Dr. Tan. Thank you so much.
Yeah.
Thank you very much.
Dr. Bouya, could I just make two comments? And I think, firstly, it's very important to make local strain measurements rather than external strain measurements.
Yes.
I've done before, but we still keep doing it. But the other point also is that much of the information we find in textbooks like Bowles has been obtained from triaxial testing using external measurements. And so probably the modulus value all anyway. And so this is, again, as Dr. Marwan said, when you use some of those published values of modulus, you can be out by factors. The thing is, of course, that having laboratory tests such as this in conjunction with energy tests such as shear wave velocity measurements, I think is a very powerful tool because they complement each other. And what I like about geophysical measurements is that any anomalies in the rock, any joints and so on, wave velocity, and so you get a better understanding of the mass modulus of the rock in that way, and that complements lab testing of this sort very nicely.
Thank you, sir.
Thank you, Professor Poulos. I think we came to an end of this pleasant and outstanding GeoTalk. Professor Poulos, it was an immense pleasure for us to have you on board with us today. Thank you for your time. I think it's very late now in Australia. We kept you waiting for so long.
Fine. Thank you very much. Look, it has been a privilege to do you. I very much appreciate the invitation to participate, and I wish you well. And as I said right at the start, I hope that we will see in the near future the evolution of society, because you people are doing fantastic projects with fantastic tools these days, and I mean, you should be exposing this to the broader geotechnical community. Thank you very much.
Hopefully, fingers are crossed.
Okay.
Thank you, everyone.
Also,
and we will.
If you allow
Yes.
me just to.
Yes, please, Dr. Mala.
Professor Poulos as well, and thank you, Hamzah, for your effort in this amazing GeoTalk, and really thank you for your time, Professor Poulos, and inshallah we'll continue the same direction. And Dr. Tan as well, thank you for your contribution. Thank you so much.
Allow us for 2 weeks approximately. We will be sharing the slides. Thankfully, Professor Poulos agreed to distribute them, as well as the recording and the certificates. So hopefully within 2 weeks' time, we will be in contact. Thank you, everyone, and hopefully to see you again in another GeoTalk. Goodbye and have a nice day.
Thank you.
Thank you very much.
Thank you. Goodbye.